So that means you can see how large this is. So today's the topic is about out of autoclave, but this is traditional autoclave. So maybe it is very contrasting information. If you know autoclave, then why out of autoclave is preferred. Okay, you can know that, right? So let's start with the manufacturing step of autoclave first, right? Autoclave. So autoclave is most the famous and the favoritely used in composite material manufacturing companies for large scale and very precise one. In the case, they usually use this one. So composite autoclave is closed molding tool that use pressurized steam to manufacture lightweight, strong composite materials. Okay? So it has 7 steps inside the autoclave to manufacture large scale composite materials. The first step is a layup of composite materials. Second step is vacuum bagging. So I don't need a detailed exploration for each step because I believe most of you already understand the overall concept of manufacturing. So vacuum bagging is second step, and the third step is autoclave curing. Okay? Autoclave curing. That means a sealed mold is placed inside the autoclave, a large pressurized oven that applies heat and pressure to the composite material. The heat catalyzes the curing of a resin, and the pressure help compress material, something like that. That means chemical compounding is being processed in this step. Okay, this is a very important step. But we can only conduct control of temperature and pressure, okay, for that process. And the step 4, after the step 4 is temperature and pressure ramp up. It's slowly ramped up, not abrupt ramp. Okay, and to help chemical compounding. And step 5 is a holding phase. Okay, the give time to the chemical react. And the step 6 is cooling phase. If the chemical compounding reaction is finished, then after that, the slowly the cool down to the phase. And the final step inside the autoclave is pressure release and unbagging. That means the composite material is now at your hand. And after cured, it is taken out of autoclave, and the post curing and machining is needed, and then inspection and quality control is the final step for the autoclave manufacturing process. So this kind of the manufacturing process. So 2 things can be noted. So first one is pressure in a composite autoclave. Usually the inside the autoclave typical range is 70 to 300 psi, pounds per square inch. That means 5 to 20 times atmospheric pressure is needed. And the temperature inside the composite autoclave is in the case of CFRP, so usually the maintained between 120 and 180, in the meantime, it needs to temperature up to 309 degrees. So I just wanted to give you the range of temperature and pressure level. Okay? It's a relatively high temperature and very high pressure, and the time is taken long Okay? That means you can think, you saw the equipment size. It means it will be very expensive. You can imagine that. But the quality is very, quality of composite from autoclave, very, very nice. Very, very nice. But for mass production, it is not good as you expect. So this is a schematic of the autoclave molding process you have been heard in previous slide. Here you can see the pressure inject pressure. Injection in this case 8 times atmospheric pressure about. And there's bagging film, vacuum line, vacuum valve, this kind of thing. So also vacuum pump is needed. This kind of the elements can be found for autoclave molding process. So people need to think how this process can be simplified while keeping the quality and to make productivity more. That means can have a cheaper composite structure after all. So the innovation is needed from this stage. So there are so many different kinds of reports and articles can be found in the literature. Okay? So this is one of the simple the report. He tried to get out of autoclave composite manufacturing process. They wanted to invent process. So I wanted to talk to you. It is not difficult to get innovative composite material manufacturing process by yourself, but you need patience, you need try and error many times, and try to get the very good data after testing and analyze and revise. So after that kind of effort, you can easily invent your own manufacturing process. It is open to you, everyone. Okay? So I just wanted to show how simple it is. Okay? This is an autoclave molding process, and this guy, so use the vacuum hot press molding process as one option. Okay, as one option. This is he wanted to claim this is good. This is his invention. He wanted to claim. Right? So actually, there's a vacuum hot press. There's a vacuum is not familiar to ordinary the material engineer, but the hot press is very common tool to material engineers. That means why this guy need a vacuum? Because a vacuum bag is usually used. Okay? If this one you have a vacuum bag, it's the autoclave. Right? So he just remove autoclave wall itself. Enclosed just remove it. And then to give pressure, they need pressure right here. So this is just very expensive because the whole space is very large. Whole space must be pressurized at the time. But this guy just wanted to press, make the high press, 20-ton press, instead of a whole pressurized environment. Okay, that means it's mechanical pressure, but it's direct press on the tool. Right? So it's very simple. So on the ordinary hot press, he just add vacuum equipment because it needs vacuum involved inside the vacuum bag. Okay? That's the only one thing he applied. And this one is a hot press molding process without vacuum. He just remove a vacuum bag. So you can think very easily this kind of things, right? So after that, he conducted a test to check the quality. Okay? This is a vacuum assisted hot press. This is SEM image of surface of composite material after cured. This is autoclave results. This strain stress. This is strain stress, the same mechanical test, right? So you can see the stress strain curve. This is from the multiple specimens. So it is not exactly the coinciding, of course, because it's testing as this variation. But it's similar like that. And this one and this one is very different. It's a little bit similar, but its level and in detail manner is different. But this is just a hot pressing without the back and back. You see that it's distinctively different from others. Okay? And the surface, the ordinary hot press, it's make a messy surface. You can see, right? And this is from autoclave, the expensive one. And this is suggested, invented. So this is much better surface, right? So I think he was excited because he got better quality after all. Of mechanical strength, this is a fractional strength. Fractional strength means fractional strength against bending moment. Okay? It is very important for composite material panels. Okay? So he checked the level of fractional strength from different manufacturing processes. This one is a vacuum hot press. It's about here. Okay? And from autoclave is similar. And this is just a conventional hot press, just far different. Right? So this is bending resistance, and the axial resistance like this. This is all average value from each the multiple testing specimens from after different manufacturing processes. For VHP case, average tensile stress from its specimen was 320 Pascal. Right? From autoclave, 335 Pascal. It's similar. Right? From traditional hot press, it's 226, much lower than it. So this is not good, but this is very comparable with autoclave. Right? And there's a standard deviation. That means how uniform after that manufacturing process. This one better than this one. It's a variation. This is better. And the average Young's module stiffness is 12 gigapascal, 13 gigapascal, very similar. But the hot press very low. So this cannot be recommended instead of autoclave. But this one is much better, a little bit slightly better than autoclave. Okay? And this is a volume percent after all. So each manufacturing process, even though they are using the same prepreg, due to final dimension will be different. So fiber volume fraction will be different. It's different. So higher volume fraction after all is a better one. So vacuum hot press case 59.2, almost 60%, very high. And autoclave is famous for its high, the fraction can be obtained is only 58. So this is still slightly better. But the ordinary one, 64. This is better, but many damage. So in compaction, this is better, but many damages, so that is weaker. The result is weak. Okay? So this cannot be used. Even more fiber volume fraction. So this is, so this guy, in conclusion, claim, okay, I invented very simple and new composite manufacturing process, so patented. But I think this has immediate drawback. What do you see? Large panel cannot be treated like this. Because of this pressure, the mechanical pressure, this will be difficult. Because this is just directly contact, the pressure loading is there. Right? If this tool has curved, in the case they want to make this tool also curved. So accordingly, there will be additional cost will be needed if this is a very big one. But the small one can be adjusted appropriately. So maybe this can be used only for small size composite manufacturing only. Then, if I was a reviewer of that paper, I would not accept the paper for publication. Why? This autoclave usually used for large scale structure, not for small scale, due to its manufacturing cost. The small part, RTM is importantly used. So this is can just replace the RTM process, not autoclave. So this kind of comparison is not suitable, I think. Okay? So anyway, there are so many different kinds of newly invented out of autoclave manufacturing processes. So just invent yourself. Invent one. Okay? If you have good patience and good focus energy, then you can do it. Okay? So I wanted to introduce what kinds of out-of-clave process existing now. Okay? It's extracted from one of legal paper. The drains extracted from this one. So I recommend you can download this one from website and you can read one. It's a little bit a large volume. Then it has a little bit detailed contents for each out of autoclave process. Okay? So out of autoclave in abbreviated is we say OOA. OOA. So this is the starting point. So RTM is also, that is not autoclave manufacturing process. So that is one of OOA, right? One of OOAs. So this is a starting point because like autoclave, this RTM is a very, very famous and very accurately manufacturing process machine. This very nice machine. It has very small drawbacks. But to overcome that kind of drawback, because it cannot be compared to autoclave application, so other OOA inventions are needed. Right? So this is already I introduced in other lecture. Right? This RTM. So this RTM has advantages and drawbacks again. So advantages many. So mostly the appreciable ones. The drawbacks are relatively small, but the most critical drawback from RTM compared to the autoclave is the size of parts, the limited size. So large parts manufacturing is not possible by using RTM. That's only one problem. And because it use very high pressure, more than autoclave pressure. So that means the preform can be damaged. It's another drawback. Okay? So as a result, it can make the kind of weak zone, like resin leaching, something like that, or broken preforms, something like that. Okay? And it's very sensitive to the location of injection gate. So it should be carefully located before application. Okay? So those kind of drawbacks can be used. So how to remove this drawback? Because this drawback is it has down mold and top mold, bottom mold and top mold. So that means it has space inside, right? So because that kind of characteristic, it has two mold to make across the space cavity, right? This bottom one, top one, bottom one, top. So what was the other original manufacturing process for composite material? It was hand open layer to make both holes, something like that. It has no top mold. It just have bottom mold. Yeah? Bottom mold only. So because it has only one side mold only, the very large structure could be manufactured. So like that, okay, let's remove top. After remove top, it cannot be exposed to outside everything. It must be covered, right? So rather than the top mold, it has cover. It's a very closely, very well sealed cover. In the case there are many airs. So what kind of need is it? That air should be going out. From inside, it must be going out. So that means outlet is needed, and the resin should be infiltrated. So inlet for low viscosity resin, inlet is needed. So you just inlet, outlet needed, and remove top mold. And this is your fiber bed preforms. So to make other things are much similar, but the small change variation applied compared to autoclave ones, because autoclave ones also has many those kind of the sheets. Sheet means distribution layer. Distribution to resin transport, those kind of display distribution and the protector layers needed even for autoclave. So they use the same things everywhere. Only thickness is different accordingly. So if you have a good technical understanding about autoclave or RTM or hand layer, in that case it's a very good opportunity to invent new one. Okay. So this is the VARTM software. It was also introduced in other lectures. So I believe you have some ideas about it, right? So VARTM also have some drawbacks. Okay. So once this is introduced, okay, large part can be possible now. But because it has no top mold, the conventional RTM must assisted by vacuum. So vacuum assisted RTM. That is VARTM. So it overcome drawback of size limitation, right? But still, there is some problem, some air trapping, entrapping. So there are some fiber compression damage. Those kind of things still encountered. So to compensate other kinds of drawback after innovation. So variations should be introduced. So there are so many variations for VRTM. That means not variation of RTM, variations of VRTM, because everybody wanted to manufacture large size of composite structure. Conventional RTM, it cannot produce, it is not fit to large scale composite structure. Okay? That's very clear, very clear. So this one has pressurized VRTM. That means this one, so this is atmospheric pressure. So this is vacuum area. So if it is perfect vacuum zone, then maximum pressure, compaction pressure will be 1 atm. Right? That is maximum. But that perfect vacuum is not possible. So that means that compaction pressure will be eventually less than 1 atm. So it make a kind of less fiber volume fraction. So they wanted to get more higher fiber volume fraction from the similar ones. So that's everyone can think its method. Maybe if we can make larger pressure difference between inside bag and outside bag, then it will be possible, right? You can, so they can make like that. This is atmospheric. Differently from previous one, atmospheric itself will not be used. It has a big case, not a top mold, just a case, just case. It is a well-sealed case. Its shape doesn't matter. Shape doesn't matter. Just need one big shell over it. And there is intermediate space there. There they have space to be pressurized by pump, right? So that means this now external pressure can be controlled at your design. You can control this one. So you can decide, okay, 2 ATM, 3 ATM, 4 ATM, as far as you need. You can control this pressure, right? And the other things are the same as the previous one. And resin, this resin reservoir and the vacuum, there is no resin pump. It will injected into due to pressure difference from this one and the vacuum. It will infiltrate. So that's why if it's just directly injected, then it is not a good result for final composite structure, because it's the bias. So it needed to be gradually distributed for whole front line. Right? So in the case, a large area of inlet areas needed. So this one, so distribution medium is needed. And this one, vacuum side. So over resin amount should be exceed. If you have a very small sinkhole, then that excessive one will rush into there. Right? So if it has a large sinkhole, then it will be greater. Right? So large area of distribution medium is needed. So you put here and there. It looks very fancy, but if you do practice by yourself. In that case, it's very simple, like a sponge. It's very simple. It's a high porous sponge material. That's all. And the sealing material is a double-sided tape. Double-sided tape. And if you cannot make sure about the leaking, then you need to make more voltages. Bolt and nut can be used. It's at your any need. You can end. So that is so simple. So simple. Vacuum. This is a vacuum bagging mold process. Okay? Vacuum bagging mold process. VARTM and a little bit variation. So release film, breathe fabric. Whenever you need some kind of function, just add a new layer. So this is just consumables. But if you can reduce this kind of consumables, that process will be cheaper. Okay? So that kind of thing is just imagination. You can think any kind of scenario. But without real practice, you cannot make sure at all. So you must do. Practice is first. Practice first. Once you have any idea, just try to practice. Okay? This one is a double vacuum bagging setup. This one has this is original, the vacuum bag environment, and it has one more vacuum bag. Okay. So this is degassing. There should be also degassing case, and this is degassing case. The degassing case means the vacuuming, and the convection piece is the outer back first, then the inner back pressure, and outer back pressure. So this kind of double vacuum bagging setup is what that kind of thing is needed. There's too much compaction may damage the preform. So wanted to step by step, not just one step. It's divided into two steps. Then it's just abrupt change, the half change is more gradual. So it's make two steps. It's nothing more. Okay? But this is also frequent. Okay? You know, this is a single backer. This usually practiced a single backer. This is a double vacuum. Single vacuum bag, double vacuum bag. After manufactured, based on the same preform, same resin, same condition. You can see the porosity. Okay. It's very different, right? This is gradual infiltration. This is abrupt infiltration. Okay? So you can make better quality. So then maybe triple bag vacuum backer will make better. Of course, it makes better. But in the case, the process will be costly. But if needed, you can do like that. Then it's your invention. It's your invention. Okay? So invention is not so difficult. Okay? So once you understand what is needed, RTM and hand layer, there's open mold, right? And the autoclave. That is triple forefather of composite manufacturing processes. You can mix it. You can get hints from ocean and see others' invention. And you can understand why that guy invented like this. But still there is drawback. You can complement that kind of insight because from that you can make your own asset. So participate in community, composite manufacturing community, and there are very tremendous many amateuristic practices, communication together. You can get a great idea. Okay? And that's just there's more variations. It's endless. This review paper extracts some of famous ones among many. This is a preview of Q. Preview is a vacuum bag only. Vacuum bag only means no pressurize. Okay. After just a vacuum, just let it. Just a temperature control only. Because it is more cheaper. This guy think maybe a top pressure control is not needed. Just after vacuum, if let it just to put for a long time, sufficient time, then productivity is low, but manufacturing cost is very small. So in case those kind of thing is needed, so it's very simple and you can see it's nothing, but it is another patent. Okay, you can see the change. This is preview cure. Okay. That it's consolidation process of OA, the pre-preg. Okay. So this is a layup just after baking, and the vacuum hold for a long time. Just the degassing stage, right? And curing, just temperature control only, right? So this curing. So after that, you can get final. So it's a cheap one. So you can make this small size of equipment in your laboratory easily. But important one, so practice it and test and investigate what kind of output you have after. Okay. This is another idea. This one, so this is fluid. This is fluid. This bed, mold bed, just floating in the fluid. That means the fluid is only one medium to pressurize the mold. Okay, that means that pressurization is not so good. Okay, that is drawback this one. But this one's the advantage is a very quick step process. As this manufacturing process name, invented name. So quick step process, that means its productivity is very high, but it can make a kind of a gradual the curvature of mold is possible. This is mold. Okay? And this cover, and this is a flexible bread, inlet outlet. And this fluid is a pressure is the kept and heat transfer fluid. That means heat control is through heating this fluid. So this is very simple. And this is this melting process. This is another version. So melting process. So melting processes means this very large structure is tried to manufacture. Right? It's divided into 2 or 3 parts or 4 parts. Divide the very bestly big structure. You can divide many divisions. Okay? So separate division can separately the molding. Okay? This part is on the molding process. It's a hot state. This one is kept cold. Okay? Then on manufactured yet. So consequently, it can be step by step. So progressed. That means the heating tool, those kind of, you don't need to heat all over the structure at a time. That means small capacity of heating is possible. That means equipment price will be low. And the heating itself or cooling itself, it takes time. It takes time. So small area for small area, that is accelerated larger than compared to larger. Okay? So this is very useful for repairing damaged composite structure, okay, rather than the newly manufactured. Anyway, this is another patent. Right? And this is SCR-IMP. This means cement composite resin infusion mold process. Okay. This one is also it has kind of the roof, right? So it can cover this large area of the okay. So vacuum bag. This is vacuum bag film for roof. Okay, vacuum bag, and this is a flow medium. This is a kind of patent core. It has a very large and thick flow medium. The flow medium is a distribution medium, as you saw in different slides. Then so why this guy put this large flow medium here? Where it was in previous one, this one, where it was? This one. This one, inlet and outlet. That means this part that injected resin should flow from here to there. It takes time, and its flow front will be small. Right? That means it has different situation, fully developed the one and unwet surface. It's a big history, most to be expected. But here, it's this one whole flow medium. It's a resin will come down from here. That means it's the resin front will be larger. That means uniformity can be enhanced. So that kind of purpose is applied here. Okay? And this is RFI. It's a resin film infusion. So it's a resin film. Yeah, this is a resin film. So from this one, can you understand what kind of difference? There is no resin. No resin. There is no resin inlet. You can see just a vacuum outlet only. Where is the resin inlet? The previous one, to make a large resin front, this kind of invention was proposed. This one, there's no resin in it. Rather than resin, this is a resin layer, the white one. Fiber, resin layer, fiber, resin layer, fiber, resin layer, something like that. After that, heat cured, and the compaction. All right? That means it's much easier to be the dry fiber wet. It's very quickly. You can think like that easily, right? If you have a focus to invent those any kinds of composite manufacturing process. So maybe this kind of manufacturing process is not rather than academic environment. I guess in industrial or the personal inventor, that kind of environment is much better status to invent new science. Because like me, the academic people just wanted to calculate first and to do something more complicated. But it's very simple idea, right? So rather than calculation, once you have a big story, then practice first and then see what happened. It's much better. This is also very smart one. Actually, this is a final product. This is final. So its name is resin infusion on the double flexible tooling, RIDFT. It's a very weird abbreviation. Anyway, that kind of things here. This is a fiber. This is a fiber. And this one, the red line, is actually it is a kind of membrane, silicon membrane. And this road fiber between the silicon membranes. And then in step 2, the seal resin infusion back, the silicon membrane is sealed. Okay? And then vacuumed. And then resin infused. Resin. Okay? Then this would be now unsolidified the state. Right? So it's kind of very flexible. The before curing status. And then just roll on the mold. Okay? And there's a seal vacuum chamber. And the vacuum from part, that means this one will be very tightly attached over the mold, right? And then demold. Then this one will be final. So this is, I think this is smart. Because this mold shape, whatever it is, it can be made. So there are endless examples like that, but the story has the same point. So just try and then make your story based on basic understanding of 2 traditional manufacturing technique plus autoclave. 2 classical one, traditional one is open hand layup mold and RTM. Then after mixing, you can make your story, how to make with destined purpose. Okay? And then practice it, and then see the results, investigate with the data, collect the data, and revise. Then you can make your own. Okay? So there is no, I think there is no the strongly governing manufacturing process yet. So still is in the beginning stage. So I already spent much time, just 1 hour on lecture here. So after the manufacturing process is introduced so far, I just summarize after that. So this is a common contents. So after download, I think this whole slide can be distributed to the participants. So you can read after. This is just a summary about that. How to test, what kind of test needed, something like that. Okay. So any question? Any question? Any question? No? So I think this is a good time to finish it today. Okay, because just one lecture is expected. The other lectures will be followed. So if you don't have any question, then thank you so much for attending today, and I'll see you tomorrow. Okay? Thank you.
And the intended inspection methods for validation of composites. Right now, sir is working on the project which cost around rupees 3 crore. So, let's have a big round of applause for welcoming our next speaker, Dr. Incheon.
क्या प्रोग्राम है पीपीटी कॉपी चाहिए चलो कॉपी दे दो पीपीटी एक चला दो ये चला दो पहले अच्छा यस नेक्स्ट एक पीपीटी कॉपी को दे दो चलाने के लिए तो वापस रीड कर दो वहाँ से
इसीलिए मैंने बोला लैपटॉप।
नो इशू, आ गया
ठीक है।
इनको पीपीटी कॉपी दे दो।
ठीक बोला है?
सर पॉइंटर पता नहीं कोई ले गया,
पॉइंट नहीं है
तो कोई ले गया। ये रखता हूँ, मैं कल मंगाया था, ठीक है। तो पता कर नीचे देखो।
ओके फाइन। So I think fine. So let we start with the thermoplastic composite processing methods and the characterizations. I think in the last couple of days already thermoset and thermoset plastic and mathematical modeling and simulations covered, and basic understanding about the composite I think covered, right? Then before going to start in detail about the thermoplastic composite materials, you have an idea about the reinforcement materials as well as a matrix. So reinforcement materials generally fibers in the form of fibers and yarn, and then we need to convert in the different structures form, that may be the UD and woven fabrics and different 3D structures preform as well. So any idea about the fibers and yarn, because there are different type of reinforcement materials, natural materials and the synthetics or man-made materials. In case of the natural materials, like you can say jute, flax. Nowadays from the synthetic fibers to the people are shifting from the natural fibers reinforced composites. So now I will start with the different type of composite and the basic classification. Maybe this is the repetitions. So the basic classification is ceramic matrix composites, polymer matrix composite and metal matrix composites. I will start pointer. So today we will focus on the thermoplastic composites, because in the last lectures thermosets, in case of the thermosets, reinforcement material may be the thermoset in case of the thermoplastic materials. For example, aramid fibers or a carbon fibers, their nature is thermoset. There is not a thermoplastic in nature, like PBO, Gylon and glass fibers. Their nature, glass fiber is in the category of thermoplastic, but aramid is a thermoset in nature. Then how we are saying it is the thermoplastic fibers, the thermoplastic composites. That is basically we are classify according to the matrix. So which matrix we are using? That is matrix, if we are using a polyester or epoxy base, then that is comes under the category of thermoset matrix. Then there are different metal matrix composite that is also used in the automobile industries, and this is the basic schematic view of the composites. Basically there is the fibers. Sometimes we are using the terminology fibers and the filament. The difference between the fibers and the filament is a continuous entity, and sometimes I will also use a yarn, filament yarn. So that means that in that yarn there is a that is the composed of multi filaments, right? Sometimes I will use the terminology fabric. That means there is the interlacement of the yarns in the different structures forms. And then I will also use the terminology UD cross ply laminates, UD laminates. That means the orientations of the yarn in the one direction, that is comes under the UD laminates. So why we are talking nowadays thermoplastic composites? Because initially thermoset composites widely popular, and the main concern with the thermoset composite is that is not environment friendly and sustainable in nature, because matrix after the 10, 15 or 20 years you can't recover again, you can't reprocess that materials so that you can use for in the another form. So in case of the advantage of the thermoplastic material is that you can get the resin or maybe reinforcement material again and you can convert it into the valuable products. That is the benefit. So it is the benefit for the to protect our environment as well. So these are the problem statement related to the thermoset composite as well as a thermoplastic composite. These are the listed merits and the demerits. The merits of the thermoset composite is the thermoset composites are a good abrasion resistance and low viscosity in nature. So easily you can prepare the composites. So handling during the thermoset resin you will not get too much difficulty, but in case of the thermoplastic composites you need to the main concern with the viscosity, higher viscosity. So viscosity is the major problem. To overcome this problem we can prepare the different preforms by using a different techniques. Maybe some of the techniques already covered and maybe some of techniques are new for you. And the merits of the thermoplastics, you can see the merits is more in case of the thermoplastic composite as compared to the thermoset composites. And demerits is the higher viscosity and solvent is also required to dissolve the thermoplastic composite and the polymer degradation, because thermoplastic composites are temperature sensitive materials, and so we need to take care about the processing temperature and everything. These are the different manufacturing techniques which we will cover one by one, the compression molding, injection molding and extrusion and pultrusion. I think the manufacturing techniques for the thermoset matrix already you have gone through the pultrusion, resin transfer molding, hand lab techniques and filament winding. These things as per your syllabus this is covered. And then thermoplastic composite, that is the injection molding and diaphragm forming. The diaphragm forming is nothing, is the similar kind of, you can say, the pressure in the hydrostatic pressure form you can manufacture the composites. And then film stacking method as well as a powder coating methods, tape length methods, these are the different thermoplastic composite manufacturing techniques. So compression molding basically is a very oldest method techniques. In this case there is nothing, we can heat the platens as per the resin, because suppose that you are resin in the resin polyethylene, then in that case you keep the temperature around the melting point. For example, as in case of SDP, the melting temperature is 120 to 122 degrees Celsius, you keep that temperature, and under the pressures, basically from the pressure you can get the mold, whatever you want a shape, that shape you can get from this compression molding. Generally the compression molding can be is used for the medium to the large part. It can be used for the hard armor applications. Hard armor can be prepared from this compression molding techniques, which is used for the protective armors, bulletproof jacket. Then injection molding, generally you can, I am giving the very basic example, toys. The component of the toys that can be manufactured from the injection molding. In that case we need to feed the pellets of the polymers and then from the extruder, and after the extruder, and the purpose of the extruder is to melt that polymers, and from after melting we can convert it in the required shape and by using a appropriate die. Whatever you want to produce a shape, you can convert it from the injection molding. Generally this is used for the mass production of small and complex small segment of automobile sectors as well as toys, and some gears you can also manufacture from the injection moldings. Then extrusion techniques. From the extrusion techniques you can extrude the pipes like PVC pipes or any thermoplastic matrix based pipes, and seeds, LDPE seeds, that is also a preform. These techniques can be also manufactured in the preforms of the thermoplastic composite, as well as some structural part you can also prepare from these techniques. Then this is the another technique, pultrusion techniques. In that case, you can from this creel you can get a filament, and then filament, and after that from the this dye you can impart a thermoplastic resin, and then you can prepare the thermoplastic composites. This is the pultrusion techniques, and the application is the beam, rods and other structures profiles can be manufactured from the pultrusion techniques. This is the comparison chart between these different processing methods, compression molding, injection molding and extrusion and pultrusion. The advantage of the compression molding, it can be used for the small part to the larger parts as well as a low tooling cost, and disadvantage is longer cycle of the time. Basically when you need to heat and then cool down, so the cycle time is more in case of the compression molding whenever you are preparing. So in that case you need to enlarge the platen size. Whenever you are going to enlarge the platen size, then the control and the alignment of the platen, that is very important. So generally this compression molding also used in the rubber industry as well. Then injection molding. Injection molding is the production rate is high and precise and limited for the small parts. Then extrusion methods, that is the continuous methods and limited for the simple profiles. Like I have said that I told in the previous slide, it can be useful for the pipe manufacturing or seeds, these kind of things manufactured from the extruded methods. Then pultrusion, that is the high strength and continuous methods. High strength materials can be manufactured from the pultrusion. Basically you can for example, you can use a carbon fibers or glass fibers as a reinforced materials, and then you can apply the resins. These are the different tau prefect manufacturing techniques. So basically whenever you are manufacturing the composite materials, you need to prepare the tau, and the tau can be prepared by the different techniques. One is the commingling process. From the commingling process you can see there are two materials. One is the reinforcement filament, another is the matrix filament. Basically I am giving the very simple example. You want to make the aramid and polypropylene composites. Aramid and polypropylene composite. So aramid fibers basically used for the strength and modulus, high modulus and high strength, and the polypropylene that will act as a resin materials. Basically that will enhance the interface between that will bind all aramid fibers, or you can say preforms together, and then you can make the composites. So in that case matrix generally used as a low melting temperature, but whenever you are choosing the matrix, that is very important. The matrix should the processing temperature of the matrix that should be lower than the degradation temperature of the reinforcement filament. For example, para-aramid is stable up to 350 degrees or 350 degrees Celsius in the normal atmosphere. Whenever you are going for the inert atmosphere, it is stable up to the 400 or 450 degrees Celsius. In that case, polypropylene melting temperature is around 160-170 degrees Celsius. So you can prepare, you can manufacture this aramid fiber reinforced composite. Then reinforcement material, then matrix. Then you need to mingle at the level of filament, and then you will convert it the preforms in the woven fabrics or any kind of structures you can convert. Like first you need to mingle the matrix at the filament level, and then that means why you are doing these things, because I told in the initial, the viscosity, the higher viscosity is the problem in case of the thermoplastic materials. So to overcome that viscosity distance, because whenever the higher viscosity, then polymer will not able to flow during the composite formation. So we are mixing the matrix at the filament level, and whenever you are going for the mixing of the matrix at the filament level, then you will get a appropriate uniform composite, void free composite. That is the target by using this commingling process. So nowadays commingling process is more popular to prepare the thermoplastic composite. Then there is another technique. This is the friction spring process. From the friction spring process, you can feed the continuous filament. Continuous filament here is act as a reinforcement material. That may be the aramid, that may be the jute, that may be the whatever you want. That reinforcements may be the natural fiber base or the synthetic fibers base as per your requirement. Then matrix you are using in the spun form, staple form. Basically staple form fibers, I think you are from the mechanical background, so sometimes you are confusing with the fibers or the filament and the sometimes yarn. So fiber staple, whenever I am using a staple fiber, that means you can assume as a cotton fibers. Cotton fiber length is short. So in this techniques, the condition is that whenever you are using any matrix, that should be in the form of staple form, yani ki short staple form. That things you can mix at the friction spinning process. From that you can make the preform, and after the preparation of the preform you can convert it as per your requirement, like woven fabric, 3D structures, whatever structures you want to prepare, you can prepare, and then you can go for the compression molding, or as per, I think in this case the most important and suitable machine is the compression molding. Then there is another technique. This is the braiding process. I think I am here giving the very simple braiding example. Even though from the braiding, these techniques you can also prepare the pipes, thermoplastic composite pipes from these techniques. And there are different type of braiding technology. So this is the only mayfold dance braiding system I am giving. But principle wise, all techniques are same. Then these are the tau prepared provide the different type of solution. For example, the resin and matrix is the side by side laying. So that means melt flow distance. Melt flow distance, what is the meaning of melt flow distance? Basically, during the composite formation, resin will melt, right? So resin will melt and the matrix, reinforced will not melt, matrix will melt. That is the resin basically. Matrix will melt and then it will go toward the inside the reinforcement materials. In that case, if you are manufacturing a side by side preform, in the melt flow distance is higher. But whenever you are shifting to the commingling process, that means the reinforcement materials and the matrix is mingles in case of the reinforcement materials. And whenever you will make the composite from this materials, so easily it will adhere the all reinforcement materials. It will all reinforcement materials or filament will stuck together. So that's why I told co-mingled is the most important techniques. So from this example you can see this is the fibers. Fibers here is the reinforcement materials. This one is the matrix, and that is used to adhere the reinforcement materials. And in the co-mingling process, whenever you will see the cross section of the yarn, the distribution of the matrix and reinforcements is like that. Then you can see the melt flow distance. Melt flow distance is lower in this case, and you will get a more uniform and having a lesser delamination problem from these techniques. So these are the different techniques. One is the commingling, frictions, and even though in ring frame you can also manufacture in the plying process like TFO process. From that you can also manufacture the preforms. This is the commingling process which I have discussed earlier, and the problem how this commingling process overcome the problem of the melt flow distance, those things I have also discussed. Now I am coming to the characterization part. Whenever you are making the preforms, then you need to confirm कि really it is happening or not, whatever your thought process. So then you will definitely go for the optical microscopic, either you will see the cross section wise or the longitudinal view of the filament. So from this cross section, whatever the thought process, how the matrix and the these are the different techniques. This one is the commingling yarn, this one is the friction spun tau prepack, and this one is the braided. In case of the braided, from this longitudinal view you can see this is the aramid, and this is one is the polypropylene. So just like is the binded is the cover like reinforcement by the polypropylene. But in that case the filament level is distance is more. But in case of the commingling, the matrix and reinforcement materials is mix at the filament level. Whenever the matrix mix at the filament level or reinforcement level, then definitely whenever you will prepare the composite materials, that will be more uniform, void free, and you can avoid the delamination problem. So these are the composite manufacturing process. From the compression molding, and in case of the compression molding, again you need to set the temperature, pressures, and processing cycle. That is very important, because that processing cycle is, again I told, it's depend on the type of materials, which type of materials you are processing. Suppose that you are processing nylon, in that case the processing cycle vary. In case of the PEEK, polyether ether ketone, then the processing cycle is vary. So as per the requirement, we need to optimize the process parameters. Even though in the modeling and simulations, you can consider this parameter, but as I am an experimentalist, so I would like to say ki, something you can think, or you can simulate in the modeling, but whenever you go for the practical and the application point of view, sometimes we need to do some jugaad. Sometimes theory not works, right? So similarly, we need to optimize at the what level? From the modeling and simulation, you can reduce that numbers. That may be the benefit of the modeling and simulation, like number of permutation and combinations you can reduce from the modeling and simulations. But experiment is equally important. Because in case of the modeling and simulation, whenever you go for the commingling and the representation of the commingling, that will automatically distribute whatever you want a distribution, that will distribute the filament. But practically is not like that. Whatever you want distribution, that will not happen, right? The mixing of the filament or reinforcement, you can say reinforcement and matrix material is not according to the theoretical calculations. That will be affect, right? And then because today I am also covering the characterization part. So is the overview, so that whenever you basically the purpose of these things is so that you can understand how we have to plan the composite manufacturing. You can manufacture, what kind of characterization needed, and how you can evaluate that composite. That is the, I think, objective of today's lectures. Then void determinations. Definitely whenever you are making the composite, then everybody is asking what is the void percentage. So how you can calculate? The very simple, basically from the rule of mixture you can calculate the theoretical density, and then you can also calculate the experimental density, and this way you can confirm the void percent. And another, from the microscopic view, you can also calculate by area. But that I will say ki density method is also appropriate, but in this case you can skip something, because you can calculate total area, and then that is another way by which you can calculate the void. Then flexural rigidity of the composites. So this is the ASTM D7264 standard. As per standard, you need to prepare the composite, and you can calculate the flexural properties of the composite, because flexural generally people are also testing the tensile properties. But in case of, suppose that I am using a composite to manufacturing this table, so in that case generally the load is in the in the cantilever principle, not like tensile load, na? If you are talking about the impact, then you will go for the impact, because you have used the composite in case of the bonded preparation of the any automobile. Then in that case impact is an important factor. So as per the requirement, you need to plan the test. So these are the failure analysis after the destructive testing, and then you can confirm what is the happening, which kind of failure is happening. According to that, you need to tune your pre-packs, and that you can also change the composition of the reinforcement and the matrix. Then ILSS, interlaminar shear strength of the UD composites. So this is the well-defined standard, ASTM D5379. From that you can calculate the ILSS. ILSS is nothing, is the applied load, peak load, and then width of the specimen across the notch, and then thickness of the composite of the materials. This is the ILS. Generally, whenever you are going through the composite materials, this characterization is done. In case of the experimental papers, along with these parameters are also helpful in the simulations as well. Now I am coming to basically I am giving the real life example, and that is also the my area, bulletproof jacket, body armor. So in case of the bulletproof jacket, not the bulletproof jacket, because bulletproof, that means ki completely proof. That is not the case in case of the bullet resistance jacket. So sometimes there is a 80% chance, 85% chance ki the human can protect from that, and 5 to 10% is still, if you have followed the every standard, but there is a chance the wearer may be injured. So bulletproof, whenever you are using a proof terminology, that is not the right for that. Even though in the public domain that is already reported the bulletproof, right? These are the different materials, and the interesting thing is that no materials, aramid, carbon fibers, gel spun fiber, UHMWP, we are not manufacturing in India. Any fibers, any high performance fibers, and there is the, like you can say, vast opportunity in case of the these high performance materials. Lot of calls, even though researchers can carried out their work in this area, high performance fiber, especially in Indian context. Day before yesterday, we got a mail from ISRO. There is a 3 to 4 project that is also relevant to the high performance fibers, because this high performance fiber based composite is used in everywhere, in the defense, in the aerospace industry, because aramid, I am giving the example of aramid, that is temperature resistance, that is used for the fire protective clothing as well, composite as well. So it is provided the high strength, high modulus, as well as the fire protection properties. So it's the specific fibers, and so it's I am not saying proudly ki we are not able to manufacture these materials. Definitely in the 5-10 years we should manufacture this kind of materials. And another is the UHMWP, ultra high molecular weight polyethylene. One of the industry, they have working in this, and they have successfully manufactured that fiber, and I proudly say ki I was working with that industry, and in my PhD work, and maybe in the within 2-3 years we will at least provide the materials for the bulletproof jacket applications. So that is the UHMWP. Basically I will also cover that materials in the subsequent slide. So these are the aramids, para aramids. You heard the aramids terminology in the last 2-3 days, but there are different aramids, para aramid and the meta aramid. Meta aramid is used for generally for the fire protective clothing, and para aramid used for the this kind of impact resistance application, because it has a higher strength and modulus. But in case of the meta aramid, strength is lesser as compared to the para aramid because of their chemical structures. Then ultra high molecular weight polyethylene. In worldwide there are 2 industries which is manufacturing the ultra high molecular weight polyethylene. One is the DSM Dyneema, and other is the Spectra. So these are the different materials, and this is work which I have carried out and already published in the research paper. So you can go through in the detail of these materials. And this one is the materials, I would like to say this is the indigenous materials, ultra high molecular weight polyethylene tape, or I can say disentangled polyethylene tape, because the processing method is different than the gel spinning methods, and this method is also cost effective. And from these materials we have also manufactured the this is the polymer, from polymer to the then tape. and from this tape we have manufactured the bullet resistance jacket armor panel, and we have successfully got the positive results, and soon we will go to that direction. Definitely that is my PhD work, so that industry will go. Now I am detached with that project, and so the methodology is like that. These are the filament, then laminates and fabric, then these are the armor. This is the combination of the soft as well as a hard armor. You can see this one, the back side is known as a soft armor and this one is the hard armor. So hard armor again is the made from the thermoplastic composite. What is thermoplastic? Basically UHMWP fibers and the reinforcement materials, either rubber or polyurethane matrix, is used to manufacture the hard armor panels. Then nowadays in case of soft armor, the shear thickening fluid is also used. Then evaluations, definitely whenever you are going for the any composites or any materials, you need to evaluate as per your application requirement. And generally in case of the bulletproof jacket, BFS is measured, back face signature is measured, depth is measured in case of the armor jackets. So what is the BFS? This is the clay. I would like to say it's representing the human body. So whenever you are, so in the back side you can see this is the clay like materials, toy clay. Then you are putting the jacket on this clay and you need to fire as per the thread level. ऐसा नहीं है कि everywhere every jacket is provided every kind of threads. Like for the pistol requirement is different. For AK-47 requirement is different. For sniper requirement is different. So according to that you need to design the jacket. You need to prepare the composites panel. So this hard armor generally used whenever you want to get the protection from the for example AK-47, and this soft armor is sufficient to get the protection against the 9mm bullet. Pistol basically, the small pistols or you can say small arm ammunition, submachine carbines, those kind of from that weapons this soft armor will able to provide the protections. So again these are the different characterizations machines used. Suppose that you want to determine the rheology of your resin, then you will go for the rheometers. Then for the melting point or crystallization temperatures or glass transition temperature of your resin or reinforcement materials, then you will go for the thermal analysis, that is the DSC, differential scanning calorimetry. And for the thermal behavior, suppose that where your material will able to sustain in the presence of oxygen, in the presence of nitrogen, then you will go for the TGA, thermogravimetric analysis. And then XRD, generally you want to see the what kind crystallographic structures of that materials and how this crystallographic structures changes with the temperature, with the processing temperature, how the orientation is affecting of the fibers. Definitely whenever you are processing at the higher temperature, that will affect the reinforcement material as well as the matrix materials. Then this is the characterization at the level of fabric. Whenever you are making the fabric from the preforms, then you need to see the what is the friction between the yarn to yarn during the preform fabrication. So these techniques you can use. And then tensile testing, sometimes stiffness is flexibility. For the testing of the flexibility you can go for the stiffness testing. For the impact evaluations, you can evaluate the low velocity impact. Generally this kind of testing method is used for the automobile industries. And for the backpack signature or ballistic evaluation, in that case real weapon is used, either real weapon or barrel. Barrel is nothing, is the weapon simulating projectiles. So this is the methodology by use you can, how you can manufacture, and the entire manufacturer's methodology is listed here. Then thermal analysis. So this is the case study. We have analyzed the para-aramid cross-ply limits. Whenever you are you want to see exactly you have tested that you have manufactured the thermoplastic composite for the aramid as well as a LDP resin. Then you want to confirm you can take the small portion of that materials and you want to see what exactly that whatever you have decided the percentage like 30% or 40% of the resin that is existing, or theoretically that is not this calculated is okay, that is uniformly distributed or not, then you can confirm from the TGA, thermogravimetric analysis, and that in that case you can confirm how much the resin or how much the fiber reinforcement material in that particular region. From TGA those kind of things you can also confirm. And what are the other constituents? Sometimes you want to see you have added some nanoparticles during the composite manufacturing. From the TGA you can see how much the percentage uniformity of the dispersion of that materials. Those kind of things you can also confirm from the thermogravimetric analysis, because in case of TGA you will use a small portion of that composite. So a small portion you can take from the 4 to 5 places and then you can see is the uniform or not. That is also a one confirmation test. Then from the differential scanning calorimetry, whenever you are going to plan a process parameter in case of the compression molding, suppose that you want to perform as you want to fabricate the composite under the compression molding and you need to set the temperature. So blindly you can't say okay is the 130 140 degrees Celsius. First you will test your material behavior. First you will test what will be the material behavior with respect to the temperature. So that material behavior you can test from the differential scanning calorimetry. From differential scanning calorimetry you can see the melting point, melting behavior of that materials, and from that you can choose that temperature. Otherwise you can also reduce the number of that cycles like optimization cycle if you have a basic characterization knowledge. Then failure analysis, I am giving the example of failure analysis of bulletproof jacket. So again, whenever you are going for any kind of failure or destructive testing, you can also check what kind of failure, what type of fracture happened after the impact or any kind of tensile testing. So according to that you can modify your resin, you can choose your resin materials as per your requirement. So these are the details, or this work is already published in these two papers, so you can refer, so you can go through from these papers and you will be understand exactly what we have done. Then disentangle polyethylene. Now I am coming to the gel spinning fibers, and that high performance laminates widely used for the armor application. All bulletproof vehicles, bulletproof jackets, all are nowadays manufactured from this gel spinning process, gel spun fibers. And I already told this is the imported materials. This is the imported materials. We are not manufacturing. All you heard na different vehicles which provide the protection against the bullet. In that case, either they are using the bulletproof glass or bulletproof gel spinning process. So in that case you can see first you are using a UHMP polymer, then you need to make the fiber. So that is not a fiber, basically I will say filament, because fiber terminology is generally used for the small quantity entities of the materials, and the filament in that case is the continuous fibers. Then you need to prepare the ply precursor. This is the precursor materials, and from this bunch of the filament you can say yarn that is passing through the resin, and from after that it will go through the drying, and then you are making the ply, and you can say this is the precursor materials. And you are whatever you are using the resin, that is the thermoplastic in nature, and generally PU based, polyurethane based thermoplastic polymer is used in as a resin applications. Then from this precursor you can also change the orientation. So maybe in the last 2-3 classes ply, different cross ply or 090 or different type of lamina and laminates things discussed. So this is the, you can say this is the lamina, and then you have prepared the laminates as per the directional like 090, 045 as per the requirement, and where you are getting the better result as So generally it is reported 0.45 and 0.45 something, that is giving a better performance. But for the product, generally as a researcher we can prove that this kind of configuration is giving a better configuration, better performance applications. But the concern is that whenever you are going in the like a shop floor, then that whatever you have prepared the combination, that should be also feasible. Suppose that you are using a different orientation, in that case waste is also more. So sometimes if you are improving it like 2 to 3%, 5%, 10%, that is not the significant for the industry point of view. So in that case you will see what will be the easy process which can be useful for the applications. So these things bother during the, like whenever you are working in the industry. As a researcher you will not bother. You will say okay fine, I am getting good result in this, then fine. So as a researcher I would say we are happy with it, but we are not concerning about the manufacturing process. So whatever you are designing the composite or the process, that should be feasible at the industry point of view. That is also we should keep in mind. So generally it is arrangement in the 0 and 90 direction. 0 and 90 in the all product we will get in the this kind of form. All are imported product, and 090 kind of around 48 or 30 layers is used, or 50 layers, and that is depend on the threat levels. I told initially, suppose that in case of the bulletproof vehicles that we need to provide the protection against the snipers, and maybe the more than that, like barrels, different type of barrels, different like 30 mm, 70 mm, different type of ammunition is there. So in that case the number of layers will increase. We need to increase the number of layers, and again that will be increase the weight. So same protection we will not provide the personnel, we can increase the weight in case of the vehicle, because we have a not problem in that case to increasing the weight. So initially I discussed that we have prepared the polymer from powder to the direct tape, and this gel spinning process, the imported material that is manufactured from the solvent or gel spinning, in that case you have to use the solvent, and this process is the solvent free. Basically it's like a melt spinning process, but not exactly melt. Maybe you are from mechanical sintering, so it's like a sintering process, just fusing the polymer powder, and then you are making the tape, and then further you are going for the drawing or stitching, and you are getting the high modulus, high strength tape. Then after making the tape you can go for this directly from this ply precursor manufacture, then you can prepare the different laminates. So this is the cost effective process as compared to an environment friendly, because you are not using solvent, but in case of the gel preparation you need to use the solvent. So this way this method is the beneficial, but the limited applications of this material is that you can use for the armor or this kind of application, where for the composite application, because this UHMWP fiber is also used in case of the lighter weight bag, like trolley bags. Now you heard about the lightweight solutions and sports bag, that is also manufacturing from these materials, because the density of the UHMWP is 0.97, and this fiber is 15 times stronger than the SS, stainless steel. Then this is the materials, and we have done the characterizations and prepared the different structures form. We have also prepared the from that tape, the continuous tape, we have prepared the yarn and then fabric, and from that fabric as well as the tape we have prepared the different type of laminates, cross ply laminates, as well as the laminates that is based on the woven preforms. So from this manual techniques we have prepared from the tape these laminates, and this is the scanning electronic microscope key, how the delamination happen, what will be the process temperature, process parameters during the laminates formation, and we have also conducted the tensile dynamic impact behavior of the materials and optimize the temperature, pressures, and structures, effect of the fabric structures, and finally we have prepared the panels from these materials. So these are the failure analysis after the tensile as well as the impact. So this is the low velocity impact, and then we have prepared the soft armor panels, and these soft armor panels we have tested against the 9 mm bullet, and we got the successfully impact resistance properties from these materials, and that is equivalent to the indigenous, that is equivalent to the imported item which is supplied by the DSM Dynama and Spectra. And here you can see the impression. This impression is very less after the bullet impact. This is the real time bullet testing, and we have interesting result find that whenever we have converted this LDP, that descent angle tape, in the woven structures, the structures in the same weight is failed. But whenever we have prepared that cross ply laminates composite and followed by the 090 pattern, and the same material, same aerial density, you can say weight of that panel, we are able to stop the bullet. So only what we have changed, we have not changed the materials, we have not changed the processing temperature, only we have changed the structures form. Only here we have changed the structures form, and we are getting the positive results. So while the composite formations, each and every step is important, structures form, preforms, preparations, everything is important. You need to take care while designing the any composites for your desired applications, whatever you are planning the applications. These are the failure modes after the destructive testings, and so the detailed study you can go through these papers. And thank you everyone for listening patiently. So any doubts and queries? So I think I have covered different segments, so it's very difficult to correlate, but definitely it will be helpful for your research. I hope या तो आपको सबको समझ में आ गया या फिर कुछ नहीं है. Fine, thank you.
इम्प्रेग्नेट कर रहे हैं फाइबर को, जो हम इम्प्रेग्नेटेड फाइबर हम 3D प्रिंटिंग्स में भी यूज करते हैं.
Co-mingling करके definitely you can use. Even though you can first start with the braiding or friction that is available in our department, so you can start. You are from NIT, na? No.
From IT, but he's asking because you have just.
You can use because matrix, in that case maybe your matrix is melting, you can definitely use in case of the 3D printing that filament.
What if we will integrate it with the thermoset and then we will read.
Thermoset basically when you want to use in the 3D printing. So how I don't know it will cure, and after that how will it will again melt, because thermoset filament already cured. Then again it will not melt during the printing.
We want to use the thermoset as resin form.
Thermoset in the resin form. In case of 3D printing.
Not in the filament form. We want to use.
That no, he want to, I think, thermoset resin in form with the fiber impregnation, yeah. But that in case of the co-mingling, you can pass just the thermoset resin from the resin and then you can use. So that will in that co-mingling you will not able to, because you will not get the filament yarn of thermoset resin, na? You will not get. PLA filament you can use, but thermoset resin filament you will not get. Only you can get the resin, and resin in case of the co-mingling you need a filament form.
commingled fibers.
Two filament you are merging, and the matrix is also in the filament form. But in case of your case, the matrix is not in the filament form, na? You just want to impregnate. From that you can use the impregnation technique. Why you will go for the commingling?
After impregnating, can a single filament can be
After
curing the resin? After impregnating,
you can make the filament.
Yeah.
You can mingle. Then again you will go for the 3D printing. So your filament will melt. Thermoset will not melt. That is already set, na? So then there is no use.
but currently we are already using a fiber filament that is already
Thermoplastic in nature.
That has been impregnated with the thermoset polymer.
Yeah. Then we are coating a thermoplastic material on that fiber.
Either you are using carbon or glass.
Yeah.
Carbon that is already coated with some thermoplastic resin. Thermoset resin. That is resin, but in commingling that will be not useful. Yeah, you can use with the thermoplastic resin in case of the commingling. But again, in case of the there is the limitation of the commingling. Some fibers that is brittle in nature, again you will get a problems like carbon or glass. It's very difficult because the commingling is done by the air. So during air, and that air followed at some 45 degrees something, so it will crack, it will fracture the fibers during the commingling process. That may create the defect. Any other? Polymer bags.
Harmful for the nature. Well, I have agreed on that. But when you are
I think polymer bags-
composite materials, that is not harmful for the nature.
No. Polymer bags is not harmful. At a particular thickness of that polymer film is harmful. Otherwise, polymer, if you are properly recycling, then you can recycle. I think 0.3 micrometer something, less than that sheet is harmful. So nowadays you are also seeing that thicker sheet is also, thicker polyethylene bag is also used. Recycle. Plastic, yeah, this that like debate. So whenever the plastic manufacturing industry, they will say we are recycling these materials, recycling 2-3 times, then it's sustainable. And if you are go for the natural kind of product, then they are claiming ki it's using water resources. This way they are saying ki this is not a recycling. Both way they can prove is the recycle. Actually, I would like to say ki as a sustainable is nothing as per the requirement. If we are talking about the 16 SDGs, Sustainable Development Goal, and the Ukraine or this kind of war is happening, then where is our sustainability? Right? So for our country, you can say protection or that perspective, we will not bother about that first. We should bother about our protections part. Suppose that they are selling and they will go for the they are after 10 or 15 years they will say we have developed this sustainable materials for the bulletproof application. By the way, that time we are able to manufacturing these materials. All man-made fiber are not sustainable if you are talking about that. The way of living of the last like 10,000 before years ago, that is the more sustainable. We are from 50, if you say from the 50 years back, we are more sustainable. Nowadays we are not sustainable. If you talk about the sustainable point of view, so we can say we are recycling 2 or 3 times, then we can increase our earth life, maybe 100 years or 200 years. In that point of view, we can say we are sustainable. But exactly if we are following the old culture, that will be the more sustainable. It is the old relative term.
Focus our research in metals.
Yeah.
What is your opinion on that?
Okay.
In
But again, in case of the metal, like rusting or those kind of happening. Nature, yeah.
Sir, it's older.
Still, if you are using natural fibers,
Like natural fibers, you can't use with the metals. Na? Natural fibers, all natural fibers you can't with the metals.
but still, your matrix material is a plastic.
Yeah, in case of plastic, but
What is the point to raise this? We are using natural fibers.
Sir, I would like to answer. If you are using a metal parts,
I'm asking. We will discuss later.
yeah, you are right. Metal is also, sometimes I am also thinking why we are replacing bulletproof jacket with the metal, but again weight is the concern. So specific product we can use this kind of materials, but yeah. But people are also working in that direction. It's not like in case of the metal, they are also using like a patka. In case of the head protection, that is also made from the metals. For the level 6 or more than level 6 or 8, they are also manufacturing in that direction. But if you talk about the impact performance and the strength, the metal, there is I think no metal which is meeting the standard of these polymeric materials. So for this specific application, I would like to say that this polymeric material is important. If you are able to achieve in case of the metal those kind of performance and properties, then that will be the very good solution. But there is a limitation in case of the metals. So I think about the metals, you know, from the mechanical background, you know well what are the limitations, because that is not my area, so I will not able to say comment on that. But yeah, initially this bulletproof jacket was made from the metallic metallic panels, but that metallic panels are around 50 kg, aerial density is 50 kg, and from that polymeric materials it is reduced up to the like 2.2 or 2.3 kg panels. But if you talk about the aerial density, that is around 15 to 16 kg per meter square. So that much the reduction. So that may be the one reason, the weight reduction. And yeah, if you are saying ki in the metals, if you are thinking that that kind of properties if you are able to get, then definitely that may be the solutions. Because I have seen some metals too heavy, but they are heavy as well as the aerial density is large. Whenever the bullet impact, all perforated. So weight is the main concern in case of the personal protection. Definitely again in the vehicles, now why people are shifting through the their composite beds vehicles? Again, fuel, they want to save the fuel. They are saying ki energy, we are saving indirectly the energy and those things, and then by weight. Then they claiming that if you analyze the life cycles of the metals as well as entire this polymeric materials, then they are claiming that energy saving or resources saving in case of the polymeric materials. So all over that is the game. In the small, like you are thinking कि एक दिन के लिए सोचोगे या मतलब 30 days की लाइफ साइकिल के बारे में सोचो तो मैं भी आप बोलो कि मेटल ही अच्छा है, बट उसका इंटायर लाइफ साइकिल सोचोगे तो मे बी द polymeric materials, why that's why they are shifting toward this polymeric or fiber based reinforced composites. So I think you got my answer somewhere, right? Okay, any doubt? So thank you.
I'm really thankful to you for your valuable time, and you have nicely, I think, connected the participants with the thermoplastic manufacturing and characterization. I have seen some of the participants have interacted with you on the thermoplastic and metal use. Okay, which one is recyclable?
Yeah, but metal I think in the later.
I have not covered metal part.
So this is Vajan. This is a small token of appreciation from our side. Thank you. So participants, we will meet again at 2 o'clock, right? So in this lab we have 3D printing setup, right? That is generally used for the part fabrications. Either you can use polymer or you can use polymer composite as well. Okay. So here this is DLP machine. This is small one. Now means in the coming month I think means more DLP machines will be available here because file is under process. But this small one is very useful for us. So we are using it I think since last 3 years, and we have made a lot of parts. So here you can see that here these are the components which we have fabricated through this DLP process. Right?
This is injector type.
Yeah, because we are also working on the other projects, right? So for that purpose we have made this extruder head. Okay, so we have added this nozzle, and you can see the quality, right? You can see the quality and finish that we have obtained through this DLP. See the surface finish, because most of yesterday I was talking about the post processing, right? Why post processing is required? Sometimes it is required to finish the surfaces, but here in DLP you can get very good surface finish and you can minimize the requirement of post processing. So this is one advantage with DLP. Okay, and here okay, keep it here. So and this is the FDM printer, right? And here we can process material in the filament form, right? If you have any polymer composite or any polymer, and if you are able to convert that polymer into filament form, then you can use this machine. Okay? Because here filament itself acts as a plunger. Do you know the principle of this? For extrusion, either we use screw extrusion based technology or we use plunger based technology, right? But here we don't have any physical screw, and on the same hand we don't have any plunger based mechanism to process the material. Then how we are able to extrude the material? My question is this: how we are extruding the material? We don't have a screw based mechanism, okay? And also we don't have the plunger based mechanism.
You spraying it?
No.
Right.
Because here what happens when we feed this material in the filament form. Vivek, please switch on this. So what happens when we feed the material in the filament form, and filament goes inside this extruder head, right? This is the pipe, okay, through which this filament will enter into the extruder head. So this filament, solid part of the filament, will act as a plunger itself. So that's why there is no physical plunger inside the extruder head, right? So by that mechanism or with the help of this principle, we are able to extrude the material in the thin wire form.
That means this must be hollow in
No, not hollow, sir. Hollow, basically this is hollow. This is solid filament, right? This is solid filament. This will act as a plunger because when it will go inside the extruder head, here we have heating mechanism, so it will melt down, right? The temperature of this filament will raise up to, for example, 200 degrees centigrade. So we have two sections. One is the solid section, and on the bottom we have melted section, right? So that solid part of the filament will act as a plunger because we are continuously pushing this filament inside the extruder head. Okay, so that's why it is very simple, right? It's very simple mechanism. When this was invented by statisticians, so they use this technology only. That's why this technology become very popular because it's simple to operate, simple to use, very simple mechanism. Only heaters are required, just right. One motor is required to push the material. So if you guess the cost of this printer, it is available only for 12,000 rupees, 13,000 rupees in the market. If I talk about the laser based mechanisms, they are costly because laser itself is very costly, the power source. So today we will show you, suppose if you have any material with you and if you have converted that material into filament form, how can you prepare the specimens, how can you prepare your functional parts using this process and using the DLP process. So this is basically the objective of this tutorial session, right? So those who do not have any idea about 3D printing, they can, that will be the new thing. Okay, this particular technology will be new thing for them. But those who know about 3D printing, this is very basic, right? But still some new information maybe is given to you. So here I am having this Vivek with me. So he will just show you. Vivek, just to go there. So what we have done basically, we need to use some software, right? A separate software is required for DLP, right? And we use separate software for FDM. So initially, this is the Cura software, right? Cura software. Cura basically is a slicer software for FDM, right? So what we do in this, because yesterday I have just spoken about the 3D printing process change. So where from we start? First we make CAD model, right? CAD model. Then we convert CAD model into STL file. Then STL again is processed, that is sliced. Then we generate toolpath. So in this software, we will import the STL file. Then we will process that STL file as per our requirement. What is our objective? If my objective is to make the just a prototype of the specimen, I will change the parameter. If I want to make the functional part, I will change the parameter. So now Vivek will tell you how to use this. We will just demonstrate the software to our participants.
So from basic CAD modeling to slide.
Yeah, not just show the
CAD modeling.
Sir, do you have the idea of CAD modeling, everyone? CAD modeling. I think most of us from the mechanical background, so everybody knows. We'll start with the STL file first, right? And one more thing, sir, I want to add. Here we have developed our own setup, right? That we have not purchased from the market. So we are developing it basically. It is under development. Yesterday I have shown you one part, right? That was having the continuous fiber. Continuous fiber. We impregnated that continuous fiber inside the region. Where is that part? No, that part. Yesterday we have shown.
Which, sir?
That continuous fiber one. In the meantime, you just prepare the software. I will just discuss with them. Yeah, thank you. So yesterday I have just shown you this part. So you can see that here what we have done, we have used fiber in the continuous form, right? But in general, what happens? Generally we use chopped fiber and resin, right, to develop the polymer composite. Okay, that is normal, right? But here what we are trying to do, we are just trying to impregnate the continuous fiber along with the resin, right? So we are processing material in the liquid form and simultaneously we are adding this fiber. We are depositing both the materials, continuous fiber and resin. So we are just developing this machine under the CRG project. So soon I think it will be developed and then we will use it with the robotic arm. So robotic arm is under installation. The installation of this robotic arm is ongoing. So we will soon try to mount the setup on robotic arm. Okay. So this is also one of the machines that we have developed in our lab only.
So robotic arm will print this.
Not robotic arm will print this because we are developing a extruder, right? That will have the capability to extrude that continuous fiber and epoxy resin. Then that extruder will be mounted on the robotic arm. This is the main objective of the project, right?
What is your objective to do this?
Sir, I cannot disclose right now, but I will tell you. Okay. in a simple way, I have just explained what is the objective. Yeah. Right. So now just focus on the screen, right? So here Vivek has taken a tensile specimen, right? So tensile CAD model, suppose he has developed in the CAD modeling software. Now that STL file has been imported in the QRA. Now just zoom it. So when you just import this STL file in the software, it automatically plays on the print bed because we have already selected the printer type, right? So we have selected this printer in the software, so it will automatically fetch the information. What are the process parameters of this printer, right? That can be monitored, or that can be varied. Second thing is what is the exact build size of the platform, because this is standard printer that is available in the market, right? So here what he has done, he has imported that STL file, and now he will process the STL file. So what kind of processing will be required? See, I can print my STL file either in this orientation or in this orientation, right? So by using my own knowledge, my wisdom, I will decide the orientation of the part. And how I will decide? Based on my requirement. What are my requirements? Whether I want to focus on the aesthetic look of the product, or I want to focus on the strength of the product. Accordingly, I will select the orientation. So we will just change the orientation of this specimen first. So suppose he has selected the part. Now what he is doing? He is changing its orientation. Now, okay, just press OK. Now its orientation has been changed with respect to the build platform, right? Earlier it was in the horizontal orientation, but now its orientation has been changed to 90 degrees, right? 90 degrees. So according to the requirement, we can change the orientation, right? According to the main requirement of the product, we can change this orientation, right? Now, once you finalize the orientation, okay, see, orientation is very, very important. Why? Because number of layers, how many layers will be there, it will depend on the orientation. Because earlier, the whole part was oriented in X and Y direction. Okay, so that time, height of the specimen was only the thickness of the specimen. Let's say 6 mm, let's say. And suppose I have opted 1 mm or 0.4 mm thickness, slice layer thickness. So how many layers I need to add to complete the fabrication of the sample? 0.4, 0.4, 0.4, so 1.2. Again 3 more layers, 2.4. Again 3 layers, 3.6. So what I told you, the specimen thickness is 6 mm. So now you can calculate, right, how many layers will be required. If you change the orientation, right, if you rotate the specimen by 90 degree, what will happen? The height of the specimen will be increased, right? Now because he has changed the orientation of the specimen, now height of the specimen has been increased. Now more layers will be required. Okay, but we should try to keep it minimum. More joints, we should avoid more joints within the specimens, because our object is to make adequate strength, right? Adequate surface toughness. So we can decide the specimen orientation by just using the wisdom only, okay, and requirement. So operator will decide. Okay, just flip it again in the same condition. Yeah. So again here change the orientation to the 0 degree. Okay, orientation is the position of the specimen with respect to 3D space, with respect to the volume, right? Build volume. So now again the orientation is in the XY direction, right? Now we will move to the next step, that is slicing. So slicing means, because as I told you that additive manufacturing is a process where we fabricate three-dimensional object by adding the materials in the layer form, right? So slicing is required to just identify the number of layers required to fabricate that particular specimen. Okay. So now you slice it. So again in the software we will slice it, and then see, we have sliced it. Now zoom. Have you generated toolbar? Vivek?
Yes, sir.
Okay. So on the same time, he has also generated the toolbar for this particular specimen. Okay. After slicing, right? Now you can see the simulation. Now nozzle is moving along the different direction to deposit the material. So currently you are having okay. So this is base layer, I think.
Base layer.
First layer.
First layer.
So first layer. So the nozzle is moving, and when it will move to the second layer, just focus on this the pattern. What will happen?
Second layer.
No, it's okay. Now just focus on the pattern, right? Now what is happening? At 90 degrees, right?
Crisscross.
Crisscross pattern. Actually, he's forming that the software is forming the crisscross pattern to increase the contact, right, between two layers. Okay, strength between two layers. So again, third layer, again orientation of the pattern has been changed, and for the next layer again,
We can change this orientation.
yes, this orientation also you can change, but I don't think in the software this
We can change it.
Okay, this feature is available. Okay, we can change this orientation. Okay, we can decide what pattern we want to use for that particular layer, so that is changeable. Okay.
So, sir, height is 3.2 and the layer
So
thickness
the
is
actual height
0.1
is 3.2 mm. So
And
what layer thickness you have?
0.1.
0.1 layer thickness here opted.
So 32 layer.
So total number of layers are 32, right? So this nozzle will divide 32 layers, and we will print this specimen. Okay, Vivek, just download toolbar and upload on this machine, right? So now what we are doing? We are going to save this toolbar, right? And we will take this toolbar in the pen drive and we will upload on the machine, right? So this is also one way to transfer the file. Or else we can connect the PC. Correct? Connection you can establish just to transfer the file into the machine, right?
So it has the hardware for that file to process.
Yeah, it has. It will automatically read the pen drive and it will ask which file you want to select or the part of the division, and then it will store. Yeah. Here we have two rollers, right? So they will rotate like this, and they will push the filament inside the extruder head. This is PTFE tube that will assist the filament. Okay, so it will go inside the extruder head.
We have flexible bed also, sir.
So this is flexible. Later on we will show. So we are just printing this specimen just to demonstrate the capability. And if you want to try, you can also try, right? If you need any toolbar by using that software and you want to print, you can.
So these are the variety of materials we have over there.
So we have ABS, we have ABS conductive, we have PLA, we have the TPU also. TPU basically is a flexible polymer, elastomer. So that you can print because you want to have some flexible properties. So you can easily make through this. Then PVA is sort of the water soluble material. Water soluble, right? Suppose you want to use a support material, right? And that should be water soluble. So you can use PVA. So long leg actually can purchase this. And under resin category, I have entered resin, epoxy, and you can see the list. So we have a lot of things to prepare the composite also. Like suppose you want to work on the conductive composites. So in that case, we need to add the CNT, carbon nanotubes, right? Or sometimes you need to add the graphene also. So those things are available because my scholars are exploring this area. So they develop their own material and they just check the printability of that material also. Right? So we have published these papers only this year. In 2024, we have published almost 10 essay papers from this lab only. Right? So so start also. No, because once the part printing is completed, right, we need to remove the specimen from the base. So if it is not flexible, then what will happen? The first layer is stick with the platform, and it will be very difficult to remove that base layer. So it will damage the part also. It will damage the printed specimen. So now what we do? We just take out this print bed in our hand and just be bend like this, and then automatically that thickness actually is removed, and we can easily remove the specimen from the print bed. So this is, I think, one of the advantage. But earlier when I was I started this 3D printing in 2014. So that time only fixed bed was available with the 3D printers. So that time we used to use some tools to remove that sticky layer. That time sometimes the parts were damaged, or sometimes the part failure were also occurred. So that's why nowadays these printers have the flexible beds. Okay. So now what is happening? Because we have loaded, so we have loaded the file, right? Now what is happening? Because it has automatically read the instructions which we have uploaded. So in the instruction somewhere the temperature is 200 degrees centigrade. So because it was in the switched off mode condition, so temperature of the extruder was 20 degrees centigrade. Let's assume, considering the cold condition in Jalandhar. Now what is happening? The heaters are switched on and they are just increasing the temperature of extruder up to 200 degrees centigrade. And similarly, base heating also we have provided to the instructions, right? So now if you touch the bed, you just come and touch the bed. The temperature of the print bed has also increased to the 50 degrees centigrade or 60 degrees centigrade, right? So now it started moving, right, along X and Y direction. Sir, more printers are actually in pipeline, and I think by the next week I will have the Bamboo Lab multi-material 3D printer in my lab, right? So that printer has capability to deal with 4 materials. Yesterday I discussed about this printer. So that Bamboo Lab printer also I have purchased. So that will be available, I think, in coming weeks. I think by the end of December. Okay. So restart again, I think, because so this spool actually material comes in this form, in the filament form. And yesterday I talked about, if you are planning to make any composite material for FDM process, what you need to do? You need to ensure the diameter. So diameter should be 1.75. Vivek, can you give me that vernier caliper? So let us check the diameter of this filament, right? See, right? See the diameter. Now it is exactly 1.75. So if you are planning to make any material, right? Any composite material, suppose you want to blend the PLA with any other filler material, you have to ensure the diameter. Otherwise, what will happen? Because the hardware will not support your filament, right? Because hardware has the openings, right, and the pipe diameter according to this one only. So that is why it is very difficult, right? it is very difficult to print composite through this FDM.
Sir, what happens if the diameter will be less?
Less, in that case, the gap between roller, that is exactly around 1.7 mm, for example. If it is too less, 1.5 mm, the rollers will not be able to push the material inside the extruder head, because there will be no contact. If contact is not, not between the rollers and filament, then they will not be able to push the filament inside the extruder head. If it is too high, then also same thing will happen. You will not able, even though feed the material.
So there is no system that that extruder means that roller may adjust and push.
No, there is no mechanism. No.
Now,
as of now, there is no mechanism, right? But if you can, propose a new mechanism, if you can explore this area, then I think it will be a new, domain of research, and you will add new thing into the 3D printers. So keep it. So now just see, because we model this specimen there, right? Now what is happening here? Nozzle is depositing material, okay, layer by layer. So once one layer is completed, nozzle lifts toward the Z directions, right? Toward positive Z. How much distance? By how much distance? 0.1 mm. Because the layer thickness is 0.1 mm. That's why we are not able to see it by the naked eyes, right? 0.1 mm. So we are not able to judge when it is going to be in the upward direction or the downward direction. So this is another tool, right? So that is used to remove the part from the sticky pad. Earlier it was made of metal, but now it is also, we have changed the material from metal to polymer. Metal, this is metal.
Previously it was.
You can focus here.
Can we know what is the time in the system?
So what time? So already they have mentioned in the software. You by playing with the parameters, you can either increase the time or you can reduce the time. Suppose if I decrease the infill density, where currently I think where have you used 100% infill density? 100%, because he had selected 100% infill density, right? Because we want to test the specimen, because we have modeled the tensile specimen, and that specimen will be used to test the strength of the material. So that's why we have given 100% infill density there, right? But if you want to reduce the density, just reduce the density. Just show the consequences. If you reduce the density, what will happen? Just Vivek, what is the current build time for this specimen? 11 minutes. Okay. Currently build 100% infill density. The build time will be 100 minutes, right? Okay, 100 minutes. But when you reduce the density, the time will reduce to the 5 minutes or 6 minutes.
So this is the input density reduced intensity and reduced to 4 minutes.
4 minutes. Only 4 minutes. So this is, I think, one of the advantage. Tomorrow we have, I think, tutorial session on the material processing. Can you just check schedule? Do you have schedule? Through itself. Tomorrow we have the one tutorial session on hands-on lab sessions for manufacturing techniques and material characterization, right? So here what we are planning, because I will, okay, we have one filament extruder with us, right? This is Yeah, this one. Sir, tomorrow we will try to make our own filament, right? This is one of the extruder, screw-based extruder. So this extruder will be used to, generally it is used to prepare the filament. So suppose you have prepared the composite. Now when you feed that composite in this extruder, it will give you filament. It will convert your material in the filament form. So this is the manufactured by this fan film, right? So we have arranged this only for you. So tomorrow we will have the hands-on session. We will try to convert the pellets into the filament form. Then we will try to print that material only. Okay. So live means right from the pellets. These are the pellets. So we will try to convert these pellets into the filament, and then we will try to print the filament through the okay. And also we have the ultrasonic, this on the back side, right? So this is very good instrument when you want to disperse the filler material in the matrix. Then this can help you in that. Okay. So we will see on tomorrow how can you use this particular instrument for that particular mixing or homogenizing the filler material in the matrix. Okay. So these two instruments I will try to demonstrate on tomorrow, right? Yeah, so that's fine. I will tell you the whole story. What is the use of this, right? And I am also having the magnetic stirrer with me. So both things I will explain to you. Then we will come to this instrument. Then we will go to that. Similarly, for DLP also we will try to develop the composite, and for FDM also we will try to develop the composite. So कल ना एक थोड़ा region में कोई फिल्टर डाल के हल्का सा ज़्यादा नहीं कंप्लीट हो जाएगा इस फिल्टर नहीं कल लाइव देखा ना एक हैंड्स ऑन लैब सेशन है दैट वी विल ट्राई टू डेमोंस्ट्रेट राइट
नॉर्मल पार्ट्स फ्लेक्सिबल है और इसमें ग्लास माइक्रोस्फीयर ऐड करने के बाद ये ग्लास माइक्रोस्फीयर ऐड किए गए और उसके अलावा रॉ भी है ये सब्सिडी रॉ ग्लास
कितने लेयर बचे हैं? What we wanted to, why we wanted to make this composite? I think to increase the dielectric constant. To reduce the dielectric constant. I will also tell you the story behind okay. Why we have done this and for what purpose we try to develop this composite. So tomorrow we will see. अभी आज यहाँ पर भी और टेक्सटाइल में भी है ना हाँ how much time is that? Just stop it.
95%. 95%.
95. मैं ना फर्स्ट ईयर हूँ सेकंड ईयर में 4 years. मेरे 5 साल हो गए हैं बोल दी आपका तुम्हारा 30 है थर्ड ईयर कंप्लीट कर तुम्हारा की शॉप कितना
We are
कंटीन्यूअस फॉर्म है तुम्हारा बता मेरा कार्बन फाइबर है उसके मटेरियल से बाकी सेम है स्टडीज वगैरह अलग है
सर
मेरा प्रोसेस डेवलपमेंट
तो बात करेंगे बाद ठीक है so now remove this specimen give it to me so sir now this part fabrication is completed right so now we have to remove this part from the print bed so now you can check we have successfully printed the specimen which we have modeled in the software. So what we have done, we have just converted our idea into reality. If you go through the injection molding route, then suppose you want to fabricate a tensile specimen, right, through the injection molding process. First you make the program, right, and that program will be loaded on CNC machine. Then CNC machine will cut the material, and then we will prepare the mold, right. Then we will just load, or we will mount that mold on the injection molding machine. Then we will feed the pellet material, then we will heat the material, then we will press the material inside the mold. So can you imagine the time? But now we have reduced the time, right? So this is one of the main advantage of 3D printing. Isn't it? So this is the benefit. So similar to polymer, you can also use, I think we have one filled polymer filament, any conductive filament?
Conductive filament.
Just take it out. Similarly, suppose you want to process the composite material, polymer composite material. The same process, same steps will be followed, right? In the market, there are some manufacturers who makes the composite filaments as well. Composite filaments. Because this is simple normal PLA material, right? We purchased one ABS conductive filament from the market. Okay, for some purpose, right? But if you want to, you are doing research like us, then you can also make your own composite material. So do you have any sample with you? Your sample?
No, sir.
No. He has actually yesterday he has successfully given his open seminar, and he is going to submit his PhD. So what he has done, he has developed the conductive filament, right, for heat exchanger applications. Heat exchanger applications. So he tested those heat exchangers. He analyzed those exchangers for their heat exchanging properties. So he did a lot of analysis and the characterization. So he did very beautiful job for research. He has published, I think, 3 essay paper in 3 years. Part time, in 3 years he has completed. Right. So you can make your own material also, but first of all you need to find out where you want to apply that material. What will be the application of that material? Then only you can select the matrix material and the filament material. Clear? Pause for DLP. Vivek? Okay, leave it. Come.
G2 box. G2 box is the software name. It is an open source software. So G2 box basic. G2 box basic is the free software, freely available. You can download it. G2 box Pro is there. You have to take the license. So we have G2 box basic. You can upgrade it to Pro just taking the license. So basic is free version. This is the interface of the G2 box, similar to that Cura software. We have to import the STL file from there. This is the build plate of that DLP. That one DLP build plate is there. It is showing in the reverse. So this is the part we have imported. This is the STL file, same dog bone shape we have imported in the G2box software. So see, this FDM 3D printer has a minimum layer height we can achieve 0.1 mm, but this DLP 3D printer we can achieve layer height of 0.01 mm. Means 10 micron layer thickness we can achieve. That is why surface finish of the DLP 3D printed part are very smooth over the FDM process, means FDM 3D printed part. This is the part we imported.
Here you can sit down, you can sit down here.
This is the part we have imported. Now slice setting is there.
So similar to the Cura, we have slice settings. We can choose parameter, we can choose resolution, right? We can choose the lot of things are there. So you can just see. You can select the machine also. Similar to the Cura.
In the Cura before slicing we have to select the 3D printer. Like here is Creality Ender 3 Pro is there. In the Cura we have used. In the G2box we have machine Photon Ultra. So Photon Ultra is there. Any cubic Photon Ultra machine is there. That is name shown here. We selected that machine. Then we have to select the resin, which kind of resin is here, resin density. It can also calculate the fabrication cost also. If you give the resin means cost, gram per ml means volume of the cost per liter of that resin. So in the print setting we can see the layer height, that is the layer height. We can go up to 0.01 layer thickness, and initially just the resin has to stick with the platform. So that is the bottom layer count, how many layer we have to make so that the resin can stick to the platform. Okay, so the count number is 2, and exposure time, how much second the UV light should be fall on that layer, that is 10 second. 10 second is the normal exposure time. For bottom exposure time it is 35 second. So this one is the bottom lift distance. After printing a single layer, the means platform will lift upside so that the liquid material can fill means in between the platform and the base material, because liquid has a density also, means viscosity of around 150 cp centipoise. If the viscosity is high, you have to lift the platform little higher so that it can take the high viscosity material will take more time to fill the gap in between the platform and surface. So 5 mm is the bottom lift distance. If we increase here to 15 mm, you will see the each layer printing of each layer. So bottom lift distance 15 mm, lift distance is also 15 mm. Now we apply to the setting. All the rest setting are means by default. Now it is saying that do you need any support, because removing the part in the FDM process it is easy, flexible material, you can remove the part, but this platform is a metal surface. It is very difficult to remove that resin from the platform, so you need that support, but the support also take much time. So here we won't take the support of that here to reduce the time only, but in actual part printing we have to take the support. Now slice at the 0.1 layer thickness. We got 2 hour 19 minute print time.
2 hours, 19 minutes. Huh?
19 minutes. It is based on the each layer.
Well, they are
Like
very small, right?
The specimen, same specimen we are printing. FDM we have printed that dog bone shape.
In 12 minutes, but it will take around 2 hours.
2 hours 19 minutes. The calculation is based on the bottom count curing second. Here that is 35 second, and 2 layer was there, and the rest was 10 second. So means if we divide that 3.2 mm to 0.01 layers, so it will be around 320 layers. 320 layers into 10 second will be the overall time of that slicing. If we save it, it will be in the .dlp format. So you can save it in any pen drive.
It is similar to the FDM case. We can also load the file on DLP, and we can just quickly release your specimen. Okay. So I think it is fine because we don't have the power supply.
So we have USR.
USB, it is connected with that?
Yes, sir.
Please connect. Keep it there only. So sir, these are the ranges actually. It comes in the water, right? This water. See, standardized, any PV. So the cost of resin actually varies according to the material. So I think this one is 1,000 rupees per liter or 2,000 per liter? This one.
Which one?
The standard one.
Standard resin grade, this is 1800 only.
1800, na? Almost approx 2,000 rupees per liter, right? Per bottle, not per liter, per bottle. And we also purchased one resin that was costing around 8,000 rupees per bottle. Flexible resin, yes. And also one more resin we purchased that was not flexible, but that was
High temperature.
having the property
And sustain.
that was high temperature value.
That is PR300.
PR300. It was also around 8,000 rupees per bottle. So the cost of the material can vary,
All thermoset resin.
right? Huh? Everything is mentioned there.
This is a flexible resin.
And this is flexible resin which we have recently procured for some purpose, right? So one is the company 3D Hydrotrack. This is a very famous company. So they can supply the material as per your requirement. So in their catalog you can find the suitable material and you can order. Right? Told you that this specimen. So this we have printed by using this material, right? Flexible one. So we can just band it, and we can again it regains its original shape after banding also. So if you looking forward toward the 4D printing application, do you know 4D printing? Anybody knows 4D printing? Expect this all because they are doing their research in 3D printing, right? So they know about 4D printing, but anybody? No? 4D printing? Have you heard 4D printing? Actually 4D basically is one additional dimension apart from 3D. Time is the dimension, right? With respect to time, material or the specimen will change its own shape under the applied stimulus. Suppose here I am applying this force here, okay? So now its shape has been changed and I can use it just for some purpose, for some application. But after a certain period of time, it will regain. Or if I apply stimulus, it will regain its shape. Okay? So you can just refer good articles on 4D printing. So this flexible material can help you. Right? To enhance the shape recovery characteristics of the specimens. Shape recovery is one of the key parameters for 4D printing applications. Okay. We need to deposit two different material, right? So if I opt this DLP, I will not able to make these kind of specimens, or I will not be able to those specimens for electronic applications. So that is why we have developed the setups which can deposit two different materials, right? Which can give us these kind of parts for possible electronic applications. Right?
So in the DLP 3D printer, how to install means how to start the process. Just take the file from there. It will be in the .dlp format. So we take the pen drive and we insert it in the 3D printer.
Speak loudly. Speak loudly so that your voice can be heard.
Okay. So after the putting the file in the machine, we have to fill the tub with the required material we want to print. Right now this is the flexible material, flexible epoxy material that we have shown there. So this is the material we have filled. We have to fill it at a certain level so that means if the large part is there, material means won't be there, means shortage of material won't be there. So we have to fill at certain level. After filling the vat with the required material,
I think software gives the amount of material required for the printing.
last time we had
दिखा दो बाद में कर लेना कल दिखाते हैं दिखा दो.
So this is the vat. We can remove it from here. Just means to clean the vat. If you have to clean the vat, means if we have to change the material, we need to clean the vat also. So we can remove that vat from here with these screws. We have to wash the that vat with the that is chemical is there. The chemical we have that chemical. That is IPA, isopropylene alcohol is a chemical name. We can wash.
Whenever you want to change the material, you can change it, but first you need to wash the tank, right? By using this chemical only. Then you can pour the second material. Otherwise, it will react, right? It may change the property.
You have to use gloves also while handling
these UV materials.
This machine. So earlier the material was prepared for isopropylene. You can clean the material with isopropylene. But right now they are making material you can use with water also, so that it will be friendly to humans. Otherwise, this material if you pour on your hand, it will react also sometimes.
So this technique actually became popular, I think, during last 10 years only, right? Earlier the machines were not available in India. Low cost machines. Earlier SLA was there, that was very costly, right? But now it has become very popular, and almost that's why more materials are coming in the market. Now people are developing. In India also, one of the company in Pune, they are making materials, customized materials. Suppose you want to develop a composite material for this, composite resin for this DLP, they will prepare for you. So some companies are coming, some startups are coming. So in the next coming 5 years, you will see the vast range of materials that will be available for the use in DLP. But it will take time, right? Because currently,
but DLP single time whole layer will be get to put a projector means UV light. You put
glass, right? At the bottom of the tank we have transparent glass, right? At the bottom of the tank we have transparent glass. Then we have this build platform, right? So this is, I think, the idea behind the planification. Okay.
as you know that three-dimensional weaving means there are different types of 3D oval structures. You have 3D solid structures, 3D hollow structure, 3D profile structures, right? And in three-dimensional weaving, yarns are positioned in three different directions, right, to produce this three-dimensional textile structure. And if you look at this different textile based preform structures, we can have oven preforms, non-oven preforms, or knitted preforms, or braided preforms for composite applications. And in all these structures, the mechanical performance of all these structures is decided by the orientation of the yarns within these particular structures. So, as a composite researcher, you must be aware about these oven preforms, right? You must have seen these oven preforms. For example, we have here, as I showed you yesterday, this is the glass fabric preform. This is the two-dimensional fabric because it has only length and width dimension. And of course, it has a certain thickness, but this thickness is, in comparison to this length and width dimension, is very, very small. And this thickness is, maximum thickness is just 2 times the yarn thickness, right? The constituent yarn thickness. And therefore only we have to use multiple layers of this particular layer, this fabrics layers, so that we can get a desired thickness in this case. So we can have different view structures. For example, we have this is the plain woven fabric, this is the twill woven fabric. So we can have again different other view based on the requirements. So these are the knitted structures, non-woven structures, braided structures. So in braiding also we can have 2-dimensional braided structures and 3-dimensional braided structures. So in 2-dimensional braided structures, you know braiding? Braiding के बारे में okay. So let me tell you that braiding is nothing but simply the intertwining of the yarns. Your shoelace is one of the braided product, right? And for the composites, we also produce the braided structures in so that braided structure may be right. That is only. So it is the intertwining of the yarns, and we can have, this is the normal 2-dimensional braid, and we can have 3D braid also. So in 3D braid, the yarns passes through the thickness, through the structure, and therefore we call it as a 3-dimensional braided structure. These are some other structures as lace and net. So if you look at the, as I said you that if you look at the mechanical performance of these textile structures, the mechanical performance is governed by orientation of these strands within the textile structure. So if you look at the reinforcements, for example this 2-dimensional fabric. So in this particular case, we can see that the yarns are placed in the 2 directions, and this fabric is 2-dimensional. It has length and width dimension only, and thickness dimension is very, very minimal, so we do not consider it, and we say that this is the 2-dimensional structure. We can also have the preform, unidirectional preform also, where majority of the yarns in the only one direction. So that is called as unidirectional preform. The other structure is 2.5D. 2.5D, so all of you know the terry fabric, terry towels. So in the terry towels, the loops are standing on the fabric, right? So therefore we call it as a 2.5D fabric.
2.5D?
2.5D means here only the loops are standing on the
no, why we are calling them 2.5?
Because it is in between 2D and 3D. Why it is in between? Because the loops you know, the loops which are only supported at the base are only are on the fabric, right, on the fabric surface. And
So can you show us
therefore,
any example or any?
so the terry fabric, the terry towel fabric, all of you know, seen the terry towels, right? Terry towels.
So do we have any sample or
Sample terry towel sample right now I don't have.
Normal face towel?
Bath towels. Bath towels, you know the.
That with fur. Okay, white tape.
Right.
That towel which we get in hotels.
Right. That is the terry towel.
Over the surface,
The loops are protruding from the surface, right? So that is the terry towel fabric. So that is the example of 2.5D fabric, right? And 3D fabrics, 3D solid fabrics. So here the constituent yarns are disposed in 3 different directions to produce this 3-dimensional fabric. And as I told you that there are variety of 3-dimensional textile structures. So for example, if you look at the classification based on the type of 3D structure, we have 3D solid structure. For example, orthogonal, angle interlock and warp interlock type of a 3D solid structure. We have 3D hollow with even surface and uneven surface. I will show you in the subsequent slides. We can have 3D shell structure. For example, we can produce a textile structure with shell. For example, the helmet, we can produce directly that type of fabric structure using the weaving machine. 3D nodal structures. So that will also, I will show you the pictures of the 3D nodal structure also, so that you based on the process, we can have 3D oval structures, 3D meter structure, 3D braided or 3D non-oval structures. So these are the different textile structures development processes: weaving, knitting, braiding, and non-oval. Based on the type of weaving machine, so we can produce this 2D weaving. You can use 2D weaving machine, normal weaving machine, to produce the 3D structures. We can have specialized 3D fabric manufacturing machine for the 3D fabrics, and another one technique is the looping technique. So if you look at the 3D fabrics, so as I said you that 3D fabrics have substantial thickness, and the thickness is many times higher than the thickness of your constituent yarns. So if you look at this particular fabric structure, so you have
how do
this.
we manufacture these fabric? Means what is the procedure to manufacture?
So I will discuss the procedure also in subsequent slide, how to manufacture these structures. So if you look at this particular picture, you can see that the thickness substantially higher thickness, and I have already shown you the 3D fabric yesterday. So this is the 3-dimensional orthogonal fabric. This is the solid structure, and it has 4 layers, 4 stopper layers, 5 weft layer. So total 9 layers are there, and we have this integrally woven 3D orthogonal structure. In comparison to this is made up of jute yarn. This is the jute yarn. Similarly, you see the same yarn we have used to produce this 2D plain view fabric, and you can see that thickness is only 2 times the yarn thickness, but here we can get a substantially thicker fabric just because of this particular typical structure of this particular fabric. Now in case of this particular 3D fabrics, 3D solid structures, there are, as I discussed with you, that there are 3 different solid structures. One is 3D orthogonal structure, another one is 3D angle interlock, and third one is a 3D warp interlock or layer to layer interlock. So in orthogonal structure means where the 3 different sets of yarns are perpendicular to each other. If you look at this simple 2D fabric, in this case you have only 2 sets of yarns. See, this is the one vertical set of yarns and another one is the horizontal sets of yarns, right? Right, only one vertical set of yarn and another one is the horizontal set of yarns, which we call warp and weft. Only two sets of yarns. But in case of our 3D solid structures, we have three sets of yarns. So one is moving in the warp direction, the another one is in the weft direction, and the third set of yarn which binds these layers of the yarns, which is called as binder yarn. And in orthogonal structure, this binder and the warp and weft, they are mutually perpendicular to each other, and therefore we call this type of solid 3D structure as a orthogonal structure. And this is the example of this 3D solid structure. So in this is the repeat unit, and we have shown here the cross section of this unit, and you can see the only one binder. But if you look at this particular fabric, across the width of the fabric, we can have multiple binder yarns. More is the binding, we can have more stiffer structure. In case of angle interlock structure, the binder moves through the structure. It goes through the structure from the one side of the fabric to the other side of the fabric, and again on the surface, from the surface to the back, again to the surface, and it moves through the thickness of the fabric at certain angle. If you look at the layer to layer interlock, here different layers are interlocked with the help of binder. So if you look at the structurally, if you look at this particular three different structures, you will understand that this particular structure, orthogonal structure, is more stiffer compared to your angle interlock and warp interlock structure. And this is the reason why we have to use angle interlock and warp interlock 3D preforms for composite materials having some complex shapes or maybe curved shapes, where you can easily bend in this particular preform structure in that particular shape. Whereas bending this particular structure, you see that this is very stiff structure. So bending according to that particular shape is very difficult. This is with the this structure is made with the jute. If you make it with the carbon or glass, it will become more stiffer, and bending this particular structure will become very, very difficult, right? So therefore, in that case, we have to use angle interlock or warp interlock type of a structure. And so we have discussed the limitations of these particular structures also. Coming to the hollow structures. So we can have, as I said you that in the classification, we can have the spacer structures connected with the core piles, spacer structures connected with oval crosslinks. Then we can classify them as spacer structures with even surface and spacer structures with uneven surface. For example, this is the honeycomb structure where the surface is not even, right? Whereas in case of this particular spacer structure, the surface is even. So, in case of this, so this is the example of spacer structure with uneven surfaces. So look at this honeycomb structure. Now, the next important aspect of this particular study is how to produce these particular structures, right? Before going further, let me discuss how to produce these particular structures. So to produce these particular structures, we need specialized weaving machine for that, right? For example, if you want to produce, let's say, this type of a structure, spacer structure connected with the oval crosslink, or this spacer structure connected with the core pile, or maybe this honeycomb type of structure, we need a specialized weaving machine for that. and this particular specialized weaving machine should be equipped with you can say arrangement to accommodate multiple number of war sheets or the yarn sheets. For example, here you see you have multiple layers of the yarns, and there should be arrangement to accommodate these multiple layers of the yarns. Further, you should have, so again these are the I cannot go in more detail about the weaving machine because it will be difficult for you to understand, but I will show you the weaving machine, one weaving machine which we have in our lab, where I will try to explain you that these particular structures, how to produce this particular type of a structure using this particular the available weaving machine in the today's situation. Because if you look at manufacturing of the 3D woven fabrics commercially is very costly. Why? Because if you want to produce such type of structures, 3D woven structures, what happens is that since you have to insert number of webs as per your requirement, and it will reduce the production speed. It will reduce the production, and therefore it becomes very, very costly. And again, one more thing is that if you want to switch from the one structure to other structure, for example, a particular loom can only weave solid structures. You cannot use that particular loom to produce hollow structures. So you should have a separate type of a weaving machine, loom-based weaving machine. To produce the solid structure, you need a separate machine to produce these hollow structures. So this is the again one 3D structure, that is 3D shell structure. So in this particular case, we can produce the shell type of a structure directly on the weaving machine by changing the fabric take-up rate, at what rate you are taking up the fabric. If you change at different places, so you can get shapes like this, and you can directly use these particular shapes and impregnate the matrix material in that particular shape, and you can get a composite material according to that shape. So this is the nodal structure. This is the 3D woven nodal structure, where such nodal network you can produce directly by weaving on the loom, and you can convert these particular structures in the composite form. So let me show you one. So this is the one of the 3D weaving machine, right? So if you look at this particular machine, you have here a creel zone where we have to place the yarn packages. So yarn, maybe so this is the glass yarn, you can have carbon yarn, right, or basalt yarn, for example. So this is the creel zone, and from there we have to take it, this particular yarns, and it will be passed through some machine components. For example, you have the hilled wires, hilled frames, and the reed, and then it will be taken to this take-up zone, and these structures are produced. And you see this. These are some of the examples of the 3D fabrics. So here, depending upon how much is the thickness, so we have to produce the 3D fabric with those many number of layers in that particular 3D fabric. So for example, you see that here you have 1, 2, 3, 4, 5 layers, 6 layers, sorry, 6 layers of the warp. So, and here you have to insert the weft yarn, the horizontal set of yarns, and in this particular opened shades to produce these particular different types of 3D solid structures. This is again the 3D spacer structure, and again to produce these particular 3D spacer structures we need a specialized weaving machine with special mechanism. Again, in case of honeycomb structures, we can have honeycombs with different cross-sectional shapes, and to produce these particular structures, what is required is in detail knowledge of the weaving technology. Detailed knowledge of the weaving technology is very much essential to produce these textile preform structures, and as we have discussed yesterday, that this preform structure largely governs the mechanical performance of the composite material. At the same time, it decides the life of this particular composite material also. For example, we have yesterday discussed that, let's say we have this laminated composite, which is very famous, where multiple layers of story fabrics are stuck together, and we impregnate these layers with the matrix material. But what happens with this particular type of laminated composites? It delaminates under various loads during the application of this composite material, and it will lead to the failure of the composite material, entire composite material. So that's why we can have this, to avoid this delamination, we can have this 3D integrally woven structures like this, where there will be no delamination, and the mechanical performance will be enhanced many times. At the same time, the life of this composite material will be again enhanced just because of this particular preform structure, right? So that's all about this particular 3D structures, and I will show you one prototype weaving machine which we have fabricated, so that you will understand how the fabric weaving is done, right?
Sir, I have one small doubt.
Please.
We are evaluating the mechanical performance of these fabrics, but can we consider the thermal aspect? Because whenever we are doing the exercise in the morning session, so our body gets hot, and in order to maintain the thermal equilibrium with the surrounding, we need to dissipate the heat. So nowadays I have referred few articles where the conductive fabrics are there. So what will be the role of this conductive fabrics, and whether it will have any impact on our health? Because this is very emerging.
So of course, but conductive fabrics and these things are different. These 3D fabrics are developed only to produce the composites for structural application, and they are not used for apparel applications. These are specifically produced to develop structural composite materials. Structural means load bearing composite materials, right? And not for the apparel application, right? Any other query if you have? ठीक है, okay.